Okay, working with vectors. So this is kind of all the basics of working with 2D vectors. To start with, equal vectors. So they have the same magnitude and direction. And they look exactly the same. So the only vector equal to 2, 4 will be 2, 4. Right, position vectors. So I spoke to you about this last time. Vectors are kind of freestanding things which you can move around. But sometimes you want to actually fix points using vectors. And what we do is we fix an origin. So position vectors start at the origin. So if we've got 2D space, origin, and we've got a point A, then we could talk about the vector which takes you from the origin to A. If the coordinates of A are 5, 4, then the position vector of A, two ways to write this. You can write this as lowercase a underlined, or this notation is quite nice. You can write it as OA with an arrow on the top, and that's equal to 5, 4. So the position vector of A is 5, 4. But you will see this lowercase notation used a bit for position vectors. Multiplying by a scalar. So if we have a vector A, then 2A will have the same direction, but twice the magnitude. Half A, same direction, half the magnitude, etc. Going back to this one here, we've got A is equal to 5, 4, then 2A is equal to 2 lots of 5, 4, and you multiply both of these by 2, which gives us 10, 8. So you're going along 5, up 4, along 5, up 4, and then you'll come along 2A. Negative of a vector, so we can also multiply it by a negative. So if my A is doing that, then minus A, same magnitude, opposite direction. In terms of how you'd multiply that, minus A, we stick with the same A, which is 5, 4, will be minus 5, 4, and that's equal to minus 5, minus 4. So you go back 5, down 4, instead of across 5 and up 4. Parallel vectors. These have the same gradient, or they're travelling in the same direction. So, for instance, A and, sorry, it doesn't look very parallel. Should we do that one? A and B would be parallel vectors. If you think about what we're doing here, when we multiplied by the scalar, you get a vector in the same direction, different magnitude. So these two vectors are parallel if B is equal to a constant, a scalar constant, times A. So it's K lots of A. So for a constant K. They could be travelling in opposite directions and still be parallel. So for example, the vector 1, 3 is parallel to 4x. If you want to find x, then this one here needs to equal k lots of this one here. So 4 times 1 is 4, 4 times 3 is 12. So 1, 3 is parallel to 4, 12. If you multiply top and bottom by the same thing, then you'll get a parallel vector. Adding vectors. So let's do e.g. A is equal to 2i minus 3j and B is equal to 3i plus 5j. You can keep them in this form if you want to, and you could just add your coefficients of I, add your coefficients of j. I tend to like working in column vectors, and I tend to teach just to convert to column vectors, but I leave that up to you a little bit. You can play around with that. So A is 2 minus 3 and B is equal to 3, 5, and then A plus B is equal to 2 minus 3 plus 3, 5. And then you're literally just adding them together. So 2 plus 3 is 5. Minus 3 plus 5 is 2. What's happening geometrically? We've got A, which is 2 minus 3. So it's looking something like that. And then B is 3, 5. I'll make it a bit shorter actually. B is 3, 5. So I'm going along 3 and up 5 to get to, for B. So B is going to be doing something like that. And so if you do A plus B, we're going along A and along B. With vectors, it doesn't matter how much you've travelled around. We're really just interested in where you started and where you finished as a vector. And that's what happens when you add them. You find this vector here. Sorry, that was meant to be red. It hasn't really come out red. So this vector here is A plus B. And this is called the resultant. So it's the result of doing A plus B. So you'll see that word used a bit. It doesn't matter if you do A plus B or B plus A. So if you did B plus A, you'd go along there, and it would still have the same effect. So addition is commutative. So B plus A is equal to A plus b, it doesn't matter which order, so commutative. And then lastly for this little bit we can look at subtracting vectors. So if I've got A is equal to 2, 3 and B is equal to minus 1, 2, then A minus B is equal to 2, 3 minus 1, 2. 2 minus negative 1 is equal to 3, and 3 minus 2 is equal to 1. What's happening graphically, just so you've seen it, so A is 2, 3, so we're going across 2 and up 3, something like that. And then if we're subtracting B, A minus B is the same as doing A plus minus B. So we're going to be doing 1 minus 2. So across 1, down minus 2. Trying to make it reasonable, but I'm not sure my scaling's very good. So that there is equal to minus B. And then that gives you this resultant here of A minus B, which is going along 3 and up 1. So A plus negative B is equal to A minus B. So as you're used to when working with numbers. So that's what's happening when you subtract them. Just one quick example. I think you'll be okay with this. But say you've got 3, 2 minus 4 plus 5 lots of B1 is equal to 11A. And we want to find A and B. Then literally do 3 times 2 is 6. 3 times minus 4, negative 12, plus 5B, 5, just timesing through by that 5, is equal to 11A. And then when you add these together, this top bit becomes 6 plus 5B. You could subtract that one from that side if you want, so you can, you can play around with these. Minus 12 plus 5 is minus 7. And then if you've got two vectors which are equal to each other, then the tops need to equal each other and the bottoms. So from here, you may get simultaneous equations, but this one comes out relatively nicely. So 6 plus 5b is 11. That gives you 5b is 5, and so b is equal to 1. And then here, a is equal to minus 7. So they're quite nice and intuitive to work with. They're not really doing anything strange. If you could look at doing, please, page 256. Try and get in the habit of underlining your vectors as well, please. I've got to nag you about that. So question 1, question 6, and then question 8 through to question 11. That's enough, but if you want a little bit of extension, have a go at question 12 and question 14. You can try 13, but I haven't done unit vectors with you yet. So yeah, So that should be quite similar, and just embed all those ideas.